Assalamu alaikum wa rahmatullahi wa barakatuh. Today we'll be looking at the different shapes of molecules. Now, if you look at the shapes of molecules, when atoms combine, they combine at different angles and in different ways to form different shapes. The shapes of the molecules are determined by the type of bonding and the way the electrons are shared and the repulsion and attraction between the protons of the electrons in the atom. And to begin with, we will look at the linear molecule. If you look at the linear shape, linear means straight, and if you look, the most obvious linear molecule that you will have is the hydrogen molecule. And another example will be HCl. And usually when we have a straight line, we have linear molecules. So any two molecules, any two atoms that are in a line will form a linear molecule. Then the next one that we have is the angular molecule. And if you look at the angular molecule, basically it is the water molecule is the most popular example because we see that the hydrogen and oxygen atoms are bonded at an angle which forms a bond angle of 104.5 degrees. And the reason for that is because there are electrons, lone pair electrons on this side, which repel the hydrogens to form an angular structure. Going further, we see that we get another shaped molecule, which is called trigonal planar. And the trigonal planar molecule is a flat molecule. As you can see here, the boron and the fluorines are all in a straight line. It's more like a Mercedes-Benz sign, as I would say, because it's flat molecule where the fluorines are bonded to the boron without any angles involved. And the contrast will be the pyramidal structure, which is the NH3 structure, where we see that the nitrogen is on the top and the hydrogens are pushed away due to the lone pair on the top, and it forms a pyramid. If we have to draw lines here, we'll see that we can form a pyramidal structure. Then another structure that we have is the tetrahedral structure. And the tetrahedral structure, the best example we can use is CH4, which we know as methane. We could also use CCl4, which we commonly call carbon tetrachloride. And we see here that this structure is a structure that has four molecules around a central atom. In this case, it will be the carbon atom. Then two more shapes that I would like to highlight in this session will be the PCl5 molecule. The PCl5 molecule is a trigonal bipyramidal molecule where we see that we have the phosphorus in the center, and then we got chlorine, chlorine, and chlorine, and these three are flat like the Mercedes-Benz sign. And on top of that, we've got another chlorine, and at the bottom, we've got another chlorine. So we have phosphorus in the center with 5 chlorines surrounding it. And the last structure we would look at today will be the octahedral structure. And the octahedral structure will be the SF6 structure, where in the center we have the sulfur atom, and around it we will have 6 fluorines, which make up the structure as in this picture here. So to round up again, we see that we will be highlighting the shapes of molecules. We have a linear molecule, which is any two atoms that are joined together. We have the angular molecule. The best example will be water. We got a trigonal planar molecule, BF3. We've got a pyramidal molecule, which is ammonia, NH3. Tetrahedral molecule, which is CH4 or methane as we know it. We've got a trigonal bipyramidal molecule, which we know is, an example would be PCl5, and an octahedral molecule, SF6. So that will be the basics of the different shapes of molecules that we will be discussing. After discussing the shape of the molecules, we will look at polar and non-polar molecules. Now, to determine whether a molecule is polar or non-polar will depend on the electronegativity of the atoms that are combined in the molecule. The electronegativity is defined as the chemical property which describes the power of an atom, rather than power, the ability of an atom to attract electrons towards itself. And we see that when atoms combine, they have electrons being shared between the atoms, and depending on the electronegativity, the electrons may be shared equally or it may be shared unequally in a molecule. So if the electrons are shared equally in a molecule, we have a nonpolar molecule. A nonpolar molecule is a molecule where the electrons are evenly spread out throughout the molecule. Then, if the electronegativity has a large variance of more than, say, 2.1, then we will discuss that a little later, where we see that we have a polar molecule that is formed. In a polar molecule, the electrons are not shared equally between the atoms. So the electrons are more towards the one side or towards a molecule with a higher electronegativity. And we will look at a few examples later. A polar molecule is also called a dipole, and I think that is important later when we look at some examples that we're going to do. Now, the first example we will be looking at is the hydrogen molecule. So, if you look at the hydrogen molecule, it is important to see how the hydrogen molecule looks. So, if we go here, using this Java applet made by PHET, and those are excellent applets which you can look at on the web. If we look at hydrogen, we see that hydrogen is the hydrogen molecule is two hydrogen atoms that are combined in a linear structure. Now, if you look at the electrostatic potential here, we see that we have the case where the electrons are evenly shared between the two hydrogen molecules. So there isn't one hydrogen molecule doesn't um, pull the electrons more towards itself than the other hydrogen molecule, because if you look at electronegativities, hydrogen has an electronegativity of 2.1. So each hydrogen has the same electronegativity and they will have an equal pull on the electrons. That's why we get this evenly shared electron cloud, so to say, between the two hydrogen molecules, and we can say that a hydrogen molecule is a nonpolar molecule. Another example which we're going to look at in our case will be the oxygen molecule, and we can also look at the nitrogen molecule at the same time. And if you look at it here, if you look at before I do the oxygen, we see that the hydrogen has a single bond with another hydrogen atom to form the hydrogen molecule. If we take oxygen as an example, we see that the oxygen has a double bond between the two oxygen atoms, and the electronegativity of oxygen is 3,5, and again here we see that the electrons are evenly shared between the two oxygen atoms, which makes it a nonpolar molecule. And the third example which we have is the nitrogen molecule. And in the nitrogen molecule, we see that each nitrogen has it has 3 electrons which are shared with another nitrogen, and this forms a triple bond between the nitrogen molecule. And again here, nitrogen has an electronegativity of 3, and the electrons are evenly shared between the two nitrogen molecules. So because we have the electrons that are evenly shared between the hydrogen, oxygen, and nitrogen molecules, we can say that they are nonpolar. They have nonpolar bonds because the electrons are not pulled to the one atom or to the other. And we can say that the molecule as a whole is a nonpolar molecule because there isn't polarity of the electrons that are shared between the atoms. Now, going further, we can see other examples. If we look at BF3 and CH4 as examples of molecules, if you take BF3 to begin with, boron tetrafluoride, we see that boron has an electronegativity of 2 and fluorine has an electronegativity of 4. So the variance of electronegativity is 2 and it is relatively high. So that's why the electrons will be pulled towards the fluorine rather than the boron. So the electron density will be more towards the fluorine side than the boron side. Now, because this is a trigonal planar molecule and it is a flat structure, we see that this bar shows us that the red side is negative and the blue side is positive. Because this is a flat structure, we can see here that the edges are red. So the fluorine side will be negative, this fluorine side will be negative, and this fluorine side will be negative, and the center of the molecule will be positive because this has polar bonds. So the boron fluorine bond in the molecule is a polar bond. But if you look at the molecule as a whole, it's a non-polar structure because it's symmetrical, and because it is symmetrical, the outsides of the molecule have negative charges and the inside is positive. So although boron tetrafluoride has polar bonds between the boron and the fluorine, because it's a symmetrical structure, it becomes a non-polar molecule. So there are incidences where we can have polar bonds, but the molecule as a whole can be a non-polar molecule. And just to show it to you at a different angle, we see it is planar structure, and we see that all the edges on the outside are red and the insides are, the center is blue. And the third example which we're going to look at will be, the next example that we're going to look at will be CH4. So we see that BF3 has polar bonds, but because it's a symmetrical structure, we see that it is a non-polar molecule. Now let's see if that also applies to CH4. CH4 is commonly known as methane. And if you look at the methane molecule, carbon has an electronegativity of 2,5 and hydrogen has an electronegativity of 2,1. So the variance is 0,4. So the carbon has a slightly denser amount. The electrons are more concentrated on the carbon side than the hydrogen side, but very slightly. So then here again, because we have a tetrahedral structure, it's a symmetrical structure. And we see here that because it's a symmetrical structure, that the outsides of the molecule have hydrogens. So there's hydrogens on the outside. The center will be slightly negatively charged, and the outside, the edges of the molecule will be slightly positively charged because the carbon will attract the electrons towards the center, and we can see here that the outsides of the molecule are blue and the center will be red. So that is the case that we can see here that again between carbon and hydrogen in a methane molecule we have a slightly polar bonds between the C and the H. So the electrons are more concentrated onto the hydrogen, to the carbon than the hydrogen. So the hydrogen side is positive and the carbon center is negative. But because it's a symmetrical structure, the outside will be positive and the center will be negative. So the molecule as a whole is non-polar, but the carbon-hydrogen bond is a polar bond. So this we see is also the case that BF3 and CH4 have polar bonds, but because the molecule as a whole is symmetrical, the molecule becomes a non-polar molecule. Now, the next case we will look at is that what occurs if the molecule is not symmetrical, it's asymmetrical. So here we have examples. Hydrogen fluoride has polar bonds. So we have the hydrogen and the fluorine. So looking at that example, if you look at HF as an example, we will see that hydrogen has an electronegativity of 2,1, whereas fluorine has an electronegativity of 4. And the variance is 1,9, which is quite a large variance. So the fluorine attracts the electrons more towards itself than the hydrogen, with the result that the electrons are more densely around the fluorine rather than the hydrogen. And here we see a classic case of a polar molecule where the fluorine side will be slightly negative and the hydrogen side will be slightly positive. So here we have a structure where we can say that we have polar bonds, and because it's not a symmetrical structure, we have a polar molecule. We look at NH3 now. And if you look at NH3, which we know as ammonia, again here we see that the nitrogen is on the top of the molecule and the hydrogens are at the bottom because of the dative, the lone pair, sorry, because of the lone pair on the top of the nitrogen, which repels the hydrogens to form a pyramidal structure rather than a trigonal planar structure. So as a result, nitrogen, because it has an electronegativity of 3 and hydrogen has an electronegativity of 2,1, the electrons will be pulled more towards the nitrogen rather than the hydrogen. And the result is the nitrogen side of the molecule becomes negative and the hydrogen sides, which are all at the bottom, will become positive. So if we do that, we can see it clearly like this. There's a red side, negative side, and a positive side. So we see here that because ammonia, NH3, is an asymmetrical structure, the bond between N and H is a polar bond, and the molecule as a whole is a polar molecule. And the third one to look at in this case here is water. And if you look at water, the bond between hydrogen and oxygen is a polar bond because oxygen has a electronegativity of 3,5 and hydrogen has an electronegativity of 2,1, and the variance is quite large between the hydrogen and oxygen, and the result is that the electrons are pulled more towards the oxygen side, and the oxygen side becomes slightly negative and the hydrogen side becomes slightly positive. So here we see that the bonds between hydrogen and oxygen are polar bonds, and because the molecule is not symmetrical, it's asymmetrical, we have a polar molecule that is formed. So here, if you look at what we've written, HF, NH3, and H2O have polar bonds. And they have polar bonds, and it is an asymmetrical structure. And because of that, we see that the molecule as a whole becomes a polar molecule. So this is a summary of the aspects which we can just highlight again, that if we have no non-polar bonds, then we obviously have a non-polar molecule, and we have the examples of hydrogen, oxygen, nitrogen, any diatomic molecule which has same atoms that are bonded together. So non-polar bonds makes a non-polar molecule. But if they are polar bonds, then what we will have to see if is the molecule symmetrical or asymmetrical. If we have polar bonds and the molecule as a whole is symmetrical, like the case of BF3 and CH4, then although we have polar bonds, the molecule as a whole is non-polar. But if we have an asymmetrical structure and we have polar bonds, then the molecule as a whole will become a polar molecule. And the examples that we have here is H2O, NH3, and HF. So, do we see that we have polar and non-polar molecules, and the electronegativity and the shape of the molecule plays a very important role to decide whether the molecule is a polar molecule or a non-polar molecule. The shape of a molecule has a very important impact on the intermolecular forces between molecules. Now, before we continue, we must differentiate between intermolecular and intramolecular forces. Intermolecular forces occur between two molecules. So if you look at this case, for example, we have a water molecule and another water molecule. So intermolecular forces will be the force between this water molecule and that water molecule. So it will be the force between this hydrogen and this oxygen between two different molecules. But when we talk of intramolecular forces occur between atoms inside a molecule. So intramolecular forces will be the force between the hydrogen and oxygen within one single molecule. So the hydrogen and oxygen force here will be an intramolecular force, and the oxygen and hydrogen force here will be an intramolecular force. But the molecular force between this hydrogen and that oxygen, between that two molecules, different molecules, will be called intermolecular forces. So we're going to be discussing intermolecular forces, forces between two different molecules. Now, continuing, the first type of molecular force which we will be looking at, and that is the strongest intermolecular forces, will be hydrogen bonding. Now, hydrogen bonding occurs when hydrogen is bonded with an atom of very high electronegativity. So, oxygen, nitrogen, or fluorine are atoms that have a very high electronegativity. So when these molecules, these atoms combine with hydrogen, we see that the electronegativity of the oxygen molecule, in this case, for example, is so strong that the electrons are very dense in the vicinity of the oxygen and very sparse in the vicinity of the hydrogen. And we see that the bond between this hydrogen, which is quite positive now, and this oxygen, which is quite negative, is very strong, so much so that the bond is extremely strong, that it is almost as each as though this hydrogen is bonded to that oxygen rather than the oxygen that it is attached to originally. So this force between the hydrogen and the oxygen is called hydrogen bonding, and it is the strongest intermolecular forces that are known. So in this case, we see that we got hydrogen bonding taking place between the hydrogen and the oxygen, and those are the forces that are between the molecules, intermolecular and not intramolecular, as we said previously. So hydrogen bonding is the strongest intermolecular force, and we can see this diagram here as well, where the hydrogen bonding occurs there and there. So the three most famous examples of hydrogen bonding occurs between water molecules, ammonia molecules, and hydrogen fluoride molecules. And because of the intermolecular forces, it affects the physical properties of the substance. Things like boiling point, melting point, viscosity, vapor pressure. Those things we won't discuss here, but we will just be discussing the type of intermolecular forces that are found between molecules. Now, another example of an intermolecular force will be found between an ion and a dipole. So here we have water, which is a dipole or a polar molecule. And as we discussed previously, we know that water has an oxygen side, which is slightly negative, and a hydrogen side, which is slightly positive. So when we have the water molecule coming into the vicinity of sodium ion, we see a bond takes place. So for example, if you take table salt, NaCl, and you put it in water, we see that the table salt dissolves readily in water because table salt is made up of Na plus ions and Cl minus ions. So here we have the Na, which I've written as a positive ion here at the bottom, and if you look at the water, it is a polar molecule, it is a dipole. So the oxygen side is slightly negative and the hydrogen side will be slightly positive. So to draw it, instead of you drawing the molecule each and every time, we can just draw an oval structure with a delta minus and a delta plus to depict which side is slightly negative and slightly positive. Now we know that opposites attract. So if we have a positive sodium ion, then the negative part of the polar molecule will be attracted towards it. That's why we'll see that the oxygen side of the sodium will be attracted to the oxygen side of the water molecule will be attracted to the sodium. It wouldn't be the other way around where we get the hydrogen side attracted to the sodium. It will be repelled so that the oxygen side is attracted to the sodium because the negative part of the molecule will be attracted to the positive ion. Similarly, we know that chlorine is a negative ion. So if we look at the oxygen, its negative side is the oxygen side and the hydrogen side is the positive side. So in this case, we will have repulsion and the molecule will reorientate itself so that the hydrogen side, which is positive, will be attracted to the chlorine, which is negative. So in this case here, we see that chlorine is negative and the slightly positive side of the dipole will be attracted towards the negative ion, and in this case it's the hydrogen atom, hydrogen atom in the water molecule. So this is an example of an ion dipole force that exists between molecules, and we see that in this case the sodium chloride will dissolve quite readily in the water. Then the third example we will look at is when we have iron in an induced dipole. So if we have, say, CCl4 carbon tetrachloride, which is in solution, and we place NaCl in this carbon tetrachloride solution, then we'll see that the salt, the table salt, the NaCl, does not readily dissolve in the carbon tetrachloride solution. And the reason can be seen here where we take this example where we have chlorine, which is a negative charged ion, and we have I took NH4, which is methane, which is a gas, but it has the same structure as carbon tetrachloride. Now, when we look at this NH4, this NH4 molecule, it's a symmetrical molecule, and it's a non-polar molecule. There isn't a negative side to it or a positive side to it. So when a negative charged ion comes into contact with a non-polar molecule, we see the case here that it doesn't readily dissolve because the electrons are evenly distributed in this non-polar molecule. But because of the collisions, what happens is that we have an induced dipole that is formed where we get a slightly positive side that is attracted to the ion and a slightly negative side that is attracted, repelled away from the ion. So we get an induced dipole where we force the molecule which is non-polar to become slightly polar so that there is some type of attraction between the ions in the solution and the non-polar molecule which has become an induced dipole for a short while. Now, another example which we could have is a dipole-dipole structure. Now, this one will be easier to work out because we see the case where we have HCl. And HCl, we know, is a polar molecule where the chlorine has a higher electronegativity than the hydrogen. So the electrons are more in the vicinity of the chlorine. So the chlorine side is slightly negative and the hydrogen side is slightly positive. So if another HCl molecule comes into contact or comes nearby another HCl molecule, the chlorine which is negative will be attracted to the hydrogen side, and we get a dipole-dipole forming where they are connected. And we can depict it using this diagram here below, where we get a dipole-dipole structure. The positive is attracted to the negative and vice versa. But if, for example, the HCl comes this way, because the chlorine and the other chlorine is negative, we'll see there's a repulsion and the molecules will orientate themselves in such a way that we have a dipole-dipole force that is formed. And that's why we see that a polar liquid will dissolve in another polar liquid. For example, ethanol, which is an alcohol which is polar, will dissolve readily in H2O, which is also polar. So we see that like dissolves in like. Another example which we will look at is when we have a dipole and an induced dipole. Now, the induced dipole we spoke about earlier is something that it is forced, that the dipole is forced onto the molecule. So here I'm just looking at an example, a theoretical example where we have HCl, which is a dipole, and we can show it using this oval structure where the chlorine side is slightly negative and the hydrogen side is slightly positive. So let's just reorientate this so that we have that. So the chlorine side is negative and the hydrogen side is positive. Now, if we have carbon dioxide, which is a linear structure, and carbon has a lower electronegativity than oxygen, then we see here that we have a case where the molecule looks like this now at the moment, where the carbon side is the oxygen side is negative, and we see that the carbon, which is in the center, will be slightly positive. So this orientation of the electrons will be in such a way that the outer edges of the molecule will be negative and the center will be positive. So when the carbon dioxide will come into contact with the HCl, then because the side closest to it is negative, what will happen is this negative will be repelled onto the other side, and it will be an induced dipole where the side nearer the chlorine will become positive and the side further away will become negative. So in this case, we have a dipole, induced dipole, uh, intermolecular force which is formed, and that is a weak force. And another example that we will have is London forces. Now, London forces take place between two nonpolar molecules. For example, one carbon dioxide and another carbon dioxide molecule. Now, because both molecules are nonpolar, we see that there is a negative side to the molecule and a positive side to the molecule. But what occurs is that when the one molecule collides with another molecule, one side momentarily becomes positive and the other side will become momentarily a negative. And as a result, we see that we have a momentary dipole forming. That we have an induced dipole force that is forming, and for a short while we see that we get extremely weak intermolecular forces that are formed, and those are called London forces. And the example of carbon dioxide, as dry ice. If you look at dry ice, we see that dry ice is has extremely weak forces between them, where even at room temperature, we see that the dry ice already sublimates from the solid phase. It goes directly into the gaseous phase. It skips the liquid phase. And that shows that the forces holding the dry ice crystal lattice together are extremely weak. And as a result, the carbon dioxide molecules readily move away from each other. So we see that hydrogen bonding is the strongest intermolecular forces. And then we get van der Waals forces, ion dipole, ion induced dipole, dipole induced dipole, and the weakest force that we will get will be momentary dipole forces, which we call London forces. So here we've discussed intermolecular forces, and we've realized that intermolecular forces play a very important role in terms of the physical properties of solutions and structures, where it affects the melting point of a structure, the boiling point of a structure, the viscosity, that means the resistance to flow of the structure, the flow of the liquid. For example, oil flows at a slower rate than water, so we can deduce that oil has greater intermolecular forces than water. That is why it has a higher viscosity, and it also affects the vapor pressure, where we see that how readily a liquid vaporizes. So that will be a summary of the different types of intermolecular forces that we have. Thank you very much for watching.